¿Ya, Cristina? Todavía no.
Sí, ya estamos transmitiendo en vivo.
Jason, I will introduce you now.
Very good.
Okay. Good evening to everyone, and thank you for being here with us. I am very pleased to introduce Dr. Jason White, a good friend of mine from Australia, as you already learned. Dr. White is currently a researcher at the Center of Excellence for Biosecurity Risk Management and at the School of Biosciences of the University of Melbourne. He is also an associate investigator at the Australian Research Council's Centre of Excellence for Mathematical and Statistical Frontiers. And let me tell you a curious fact. Right now, he is about to start the talk at a little bit past 9 a.m. on Wednesday, October 21st. So, you know, that is tomorrow. So technically he's speaking to us from the future. So that's pretty amazing. I will leave you with our guest speaker, and he will tell us about frustrated mathematical modeling and changeable destinies. Analysis of model structures to support useful results.
Thank you for that introduction, and it's a pleasure to be invited to speak to your seminar series. If you were tuned in a little while ago, you would have heard me talk about this picture. Sums up how I feel about interdisciplinary research and application of mathematics. We maybe can't see all the way to where we need to go, but there's certainly a lot of opportunity there and maybe expectation about what can be achieved by the application of mathematics to new areas. This is a Jupyter notebook, so I'm going to skip over sections just depending on time. I'll start my timer. So we're going to have to go through a few preliminaries just to make sure we're all speaking the same terminology. This is how I think about modeling. I talk about model structures, and that's useful because of the terminology of the area. And I just want to represent that graphically. So we can talk about a structure is a collection of models. And if we have a parameter set, then each point in the parameter set is associated with a particular model. So the resolution isn't great on this, unfortunately, but let's say we're in the gray rectangle is some huge class of mathematical systems. And within that, we might have a structure of these related systems, which say S1 has a parameter set theta1. And the useful thing about thinking about structures is that we might summarize a structure in this sort of representative space where we say, we talk about these phi vector or phi, depending on your accent, which is called invariance. And what these do is summarize the output of a general system in.
I'm sorry to interrupt. Yes? Can you make it the image bigger?
I can try. It seemed to get bigger and then smaller. Is that any better?
Yes.
Okay. So this collection of systems in this structure, each individual system, we can kind of summarize the content of that structure with some features, invariance. And that's quite useful because we can work with a representative of that structure. So sometimes people use models in different ways. I'm going to talk about a model is an element of the structure rather than something that's the state space structures, you probably, there's an awful lot of terminology, and it's probably because a lot of these ideas have come up in different areas and they're not necessarily talking to each other. But for today, I'm going to talk about the state space structure is we have maybe three different variables that are of interest to us. We might have an input, which we apply to a system, which might be you inject into someone's blood a concentration of drug, so that's an input to their system. states, which might be, say, the concentration of the drug in the liver, the blood, the kidneys, or it could be the states, as we have now during a pandemic, of infected and recovered people in the population. And we have something that we can observe. And usually we cannot observe all of the states. So we're operating under a limited information, and the why is what we can actually observe about the system. And we might have a parameter set, capital theta, and as I said, we take any element of that parameter set gives you a particular model in the structure. And this might not be a one-to-one mapping, and that's really the core of the problem of testing structures for identifiability. I will have to change that zoom, unfortunately, a little bit. So, sorry about this. Okay, so I did a little bit of work with malaria modelers, and there we have a sort of natural relationship between these abstract concepts, where we have a parasite can exist in one of 3 different states. The life cycle of malaria is a 48-hour cycle. I won't go into all the biology here, but basically we have transitions between these 3 different forms of the parasite before it bursts out of a cell to go and infect other cells in the bloodstream. And the states are, say, the counts of parasite in these different alternative forms. We can only measure some portion of the parasites, which is those that are circulating in the blood, and the input is the applied treatment. So there's a ubiquitous problem, I suppose, in applied mathematics. At some point, we collect data, we build a model, and we want to estimate parameters. And people sort of assume that if you have good enough data, that you can get to some satisfactory result from the parameter estimation problem. It's not always the case, as some of you may have found. If you haven't found that, you've been very lucky. You have well-posed problems. But we could talk about identifiability in an idealized setting where we imagine that we have an infinite and error-free record of data, that we have a model structure which is a correct representation for the physical system that we're studying, and there may be further conditions that depend on the specific type of structure that we're looking at. But basically, if we have a structure that lacks the property of structural identifiability, then it's very, very unlikely that we will be able to get a unique estimate of our parameters, of our assumed structure. And that can be very difficult for us to deal with, depending on how many alternative solutions that the parameter estimation returns. But the point of testing the structure first is we don't require data. We can say something about the likely frustration that we're going to face. I mean, if all you wanted to do was to fit a model through a cloud of points and make predictions interpolating, then maybe it doesn't matter what the parameters are. But in some cases where the world changes and we want to ask what if questions, then these different parameter vectors may lead to very different predictions. And if we don't know which is the true parameter vector to use, or the best approximation to the true parameter vector that we don't know, then we're unable to go on and make predictions if the predictions that come out are very divergent. And I have an example here from cancer modeling, which basically this is a numerical case to show the point about the growth cells, and the axis here is it's a log 10 axis, I think. That these 2 different parameter values, they seem to give you pretty much the same kind of expected trace of counts of cells during some treatment period. But if you were to use the same parameter values here in a period where you have an intervention, you'll get very different predictions for how these cells are going to grow over time, the number of cells that there will be over time. And that's very inconvenient to you if you want to judge the success of this intervention, but depending on the parameters, you'll get very different results. So that's, maybe we'll skip over some other stuff in the interest of time. There are sort of nicer things we can do maybe with numerical, like generate simulated data and fit models, and we make assumptions about how much data is available and how much noise there is. And while that might show you that you don't get unique estimates, it doesn't it diagnoses the problem, it's a therapeutic device for the problem, because it maybe isn't going to tell you what you need to change about your structure so that you'll get an inverse problem that is more well posed, that is more likely to produce a unique estimate. So the numerical stuff is probably what we're all very comfortable with, I suppose, because it's part of our undergraduate courses maybe. And the identifiability is something that sort of tucked away on the side and is not always worried about. It's sort of a subordinate to the modelling effort. And my argument is that if we put it up front at the beginning, when we first propose a model, we're more likely to get a good result from our model. Into looking and demonstrating the concepts with an example. This is a sort of general idea of a representative system for a structure of models. So this is in a very general form. We have an ODE system here, x dot, so the time derivative of the states x. And the uncontrolled state here is that sort of complicated enough. And within this, what's very interesting about maths, I suppose, is that we have different subclasses of model structures depending on the systems we're looking at. And we might not analyze these the same way. If we're looking at positive systems, for example, which is when we look at physical situations, we may have non-negative values. So we're looking at positive systems. And then if we have mass is conserved and not destroyed or created, then we even have a subclass, which is a compartmental systems, which imposes other restrictions. Maybe I won't go into all the technicalities, but in terms of the central definition of what we're looking for here, I use a traffic light kind of system, which is we're trying to find all of the theta prime such that over some particular time set exactly reproduces this idealized data that I talked about earlier. So that's the idealization of the test. And there is three main possibilities we could have. You either have a unique membership of this set, which is green. There's the green light, all systems go. The amber light is that we may have a set that has solutions that are separated from each other, so that within a neighborhood of any of these solutions, there's no other competing solution. And you might know something a priori about your system, that you know the parameters must be within a certain range, and if these potential solutions that we find are separated from each other, you can exclude some of them as infeasible solutions and narrow down to, well, this must be the one that we use for prediction. But there's the red light is, well, a hopeless case, because we have a continuum of parameter values in our parameter space that are all equally as good as each other, and there's no way of being able to distinguish between values on a continuum. And that's a pretty serious inconvenience, because in that case, we may have just wasted all of our time collecting data. And I do speak from experience. When I first came across this problem, it was after about 6 months in a biochemistry lab, doing a lot of lab work very slowly, because I was a maths PhD student, not a biochemistry PhD student at the time. And the fact that the algorithm, the search algorithm, was crashing when I knew that the code worked, and puzzling at the time, and that's what led me to realize that maybe this identifiability problem was actually going to stop me getting anything useful out of that time spent in the biochemistry lab. I'll just talk about the alternative. I mean, the definition above, maybe I'll show that key equation, is not very easy to work with. And what's easier to work with is this idea of these invariants I talked about earlier that define the systems in our particular structure M. And so we can reduce that functional relationship at the heart of equation 4 above to something in terms of invariance in equation 5. And the membership of this set is exactly the same as what we had in the previous definition. But here we're dealing with algebraic quantities that we can extract from our model structure using a variety of different methods, maybe too many different methods. There's a lot of choice, and we can then go on and classify our structure and say something about the properties, the likely parameter estimation. I guess from a more recipe-based point of view, the way that we go about testing the structure, once we've specified the structure and all of its details, we extract invariance from it from some particular method. And this is what I like about the linear time invariant structures, is that it motivates the study of Laplace transforms, which is sometimes not an easy thing to get undergraduates enthused about, but here's a nice application of why it's quite useful. And I'll talk a little bit about that through the example. We find these alternative invariants, which are a function of our alternative parameter that we want to solve for, the theta prime vector, form the equation, solve the equations, and then how many members, what's the membership of the solution set. So I think what we'll do is we'll get into an example, and I did work with a very senior mathematician who couldn't believe this result with her own eyes. Compliment. It maybe means that some of these ideas are really not that obvious, which is probably not good, because we want everyone to be thinking about the quality of their models and using their time effectively. Robust science. It's a very simple state here. It's in this state vector x, a very simple ODE, which is you have decay of x1 to become the state x2 at a certain rate, and then there's a sort of flow of x1 into x2 as this drug is metabolized to its alternative form, and then that is excreted from the system at some particular rate, and that's why we have a negative on that coefficient. But for simplicity, we'll just take a fixed initial condition, and let's say, as is often the case with these biological systems, you cannot observe every facet of the system, but we can observe the concentration of x2. Full 3-parameter structure. Now, I've left the commands in here, so if you were interested in how you would use Python for this, one day this will be published. I just haven't found the time to do it, but that's the plan, is to make open source tools available. So without too much of a startup cost, you could put in a model at the top and run through some of the steps. This idea of the Laplace transform gets us to invariance. That the tradition, I guess, in engineering is to talk about a transfer function or a transfer matrix, which you relate the Laplace transform of the input to the Laplace transform of the output through a transfer matrix. And that summarizes a lot of the features of the dynamics that we want to work with. So I won't really go through the derivation, but it's a fairly straightforward thing to do to take the Laplace transform of a linear ODE system, as I'm sure you all know. We scroll through, there's different steps here in the code that extract these invariants. So we have out of this system 3 features that summarize that idealized infinite trace of output. The sum of 2 of these rate constants product and another parameter occurs by itself. So in keeping with the recipe that I showed you earlier, and I'm mindful of time, we create sort of an alternative vector of parameters just by replacing, say, alpha with A and beta with B and gamma with C. So there's this is our phi as a function of theta. This is the phi as the function of theta prime. We form the equations, and then we can go on and solve the solution set. This you could do by hand, I suppose, but in terms of writing code, I wanted to have all the steps coded up. So what's the payoff? The payoff here is to get the theta prime parameters, the solutions in terms of their original parameters theta. We see that there's 2 possibilities here, and they show that there's basically an exchange in the positions of alpha and beta between these 2 solutions. So we can get an exact value for C. C is the parameter C. So as far as alpha and beta go, there's no certainty there. There's 2 possibilities. And so if your simple question stated at the start was to estimate the rate constants from some output function, then you can't do anything with this problem to have a unique solution. And so based on our rules, having 2 solutions, we would say that this is structurally locally identifiable, which then gives us that problem of choice. Which is the true value out of these 2? Right, maybe is this a good time to ask if there's any questions before we sort of dig further into it?
¿Alguno quisiera consultar algo antes que él continúe? I guess you can go ahead for now.
Okay. All right, so as time is short, perhaps what I will do is just give a bit of the flavour of looking at controlled systems. And the uncontrolled system is a good place to start, but often we have an applied input or choices of inputs that we could apply to excite some system or stimulate some system, and then we observe the response. So the problems do get more challenging because of having that choice, and we now have that depending on the input you apply, you may get a certain amount of information out of your system, and a different input may give you a different amount of information that's more useful. And this is one of the challenging things. So what people may choose to do is to say, let's assume that we could apply any input to this structure and observe any possible output from that, and then base our identifiability analysis on that. And the problem with that is, in reality, with humans, you might not, for ethical reasons, be able to apply any concentration for any duration to that person. Maybe they will get up and leave the lab because they've had enough of having injections, or maybe it's just it's not good for their health to receive very high concentrations. So this is something that one of these sort of edge cases maybe of the identifiability problem is that we need to be able to make a distinction between having how much information we're actually trying to get out of the system, and to treat the system as if we could get all the information possible for any input is not always an appropriate thing to do. So I guess this is a sort of simple statement of a linear time invariant structure. So it can be written as this sort of matrix equation, and it's similar to before, it now has the inputs feature in it, which of course drive the states, and then the states drive the output. I talked about before about this transfer matrix, which is mediating the effect of the input on the output. Well, in the earlier case, it was determining the effect of the initial conditions on the output. Now we have that transform of the input. So of course we require that this exists, which in most cases this input is chosen and it does exist. It's not an exponential of an exponential, for example. So in a lot of cases, this does exist, and it's appropriate to form these matrices again and to extract from those the invariance from those suitably processed. So I do have maybe a little bit of time to go through another example to give the flavour of it, and this has come out of work with some malaria collaborators. I was sort of asked to go along to a workshop, not knowing that much about malaria, but basically to give you an idea that this is an approach that can scale up to not just toy trivial systems, but to more complicated systems. This one is, we've got a parasite count and a concentration of drug, which is acting on the parasite. I mean, this is the simplest of these kinds of things, but there's also a decay in the drug, and I'm using that as an input here because it sort of fits that format that I showed before. It's not something that is part of the state's ODE because of this time dependence. If I want to continue to treat this as a linear time invariant system, so I treat this time varying bit as an input, and this matrix here is because I'm not able to observe all of the 48 hours of the life cycle, but I can observe some fraction over 26 hours of the life cycle. But I can observe the drug at any time by drawing a sample from the patient. So again, this is sort of a bit formulaic now. We set up a theta vector and a vector of alternative parameters and set up the Laplace transform, which depends on this input, which I specified earlier. So again, there's some nice things you can do in an educational perspective to look at the domain of convergence of the Laplace transform, because it's good to know the limitations of the tools you're using. So from that, we can sort of get down to these kinds of transfer function expressions. And then from the simplified form of these, we're getting the coefficients much as we did before. And okay, I'll skip over some of the sort of calculation aspects of it, which you wouldn't do by hand once the system gets sufficiently interesting. Form the coefficients, form the test equations, and then go on and get a symbolic algebra routine to solve them. So to talk about the solutions here, it looks like there's one family of solutions. And remember, this is our alternative vector, and this is the original vector theta, that we have a one-to-one correspondence between the alternative vector and the theta parameter for most of these guys, except when we get down to here, we get this parameter is a function of some other parameters. And so this is maybe where the analytical approach demonstrates its value compared to plugging in equations into an ODE solver, generating simulated values with some randomly chosen parameters, adding noise and doing a parameter estimation that way, is that here we can see that if we reparameterize appropriately, we might be able to get a better result when we fit our model. So as it stands, this is an unidentifiable model, but by a suitable reparameterization, we can change it so that the structure has a better property. It's now going to be globally structurally identifiable by an appropriate replacement. So if that's the takeaway from today, is that you get more insight by an analytical inspection of your model structure than you will get by simulation, because it's still not done in a very widespread manner from what I've found in a lot of different applications. Even been editorials written about this in say, I think it's the Bulletin of Mathematical Biology, talking about the reproducibility problem in computational biology. And some of that might be that if you and your collaborators have the same model using different search approaches, then you can end up with different sets of parameters. And of course, that's to be expected if the model structure is not identifiable to begin with, because we know that underlying any response surface is going to be a multiplicity of equally valid parameter values. So I think if you were kind of interested in that, you would be able to find references easily enough on that. I have a preprint, well, a pre-publication version of a book chapter which steps through a lot of the concepts and identifiability that I'd be happy to pass on. If anyone had an interest in getting a sort of more of a familiarity with some of the basics. But I think given the title that I set, is that it's maybe appropriate to give you a sense of that there is a lot of challenges still in the field, and there's still not just getting people to think about these kinds of problems, but there's actually open problems that are still, I think, quite interesting. And that is that this is some of the a sample of simulated data from the biochemical experiments that I talked about from my lab days. And what we have here is this sort of switching behavior. So you have some chemical reaction going on for a certain period of time, and then you change the solution to something that does not have the chemical substance in it, and what you get is a breakdown. And I show this just to illustrate this as abrupt change in behavior of the data. And so the structure that we use to model this has to have a switching behavior in it. And once we're into that kind of regime, a lot of the tools from the past don't work anymore. And it's a kind of a historical curiosity that, and maybe because there were plenty of non-switching systems to look at, that people were busy with those, and it's still an active area of research in structural biology, I suppose, systems biology, that people have big models that they're still struggling to analyze with the classical methods, or even newer methods. But this is a sort of a whole other island off by itself, which is the switching system. And so that's sort of one particular lab apparatus. And maybe you think, well, okay, that's a very specialized kind of area. But with some of these colleagues who were disease modelers recently, we have a review paper on various aspects of mathematical modeling and identifiability. As a small part of that, I can pass on a reference. It's Epidemics 2020. And this is a sort of the SIR model in a simplified form, just to give you a sense of how some of these problems are maybe more relevant to our lives than you might have thought when you were reading the abstract. Is that, let's say we've got these parameters of particular interest here that are determining the rates of recovery or of susceptibles being converted to infectives. And if we just consider the left side here, we will have multiple different parameter pairs can produce this same output curve. Okay, so it's not an identifiable system. But why does it matter? Well, let's say we were to introduce at this time here with a dotted line some kind of intervention. And we were to say, like we had in Melbourne, okay, everyone's going to start wearing masks. By law, you can't leave the house without a mask. Then in this case, the behavior is going to be very different on how effective your intervention is going to be in reducing the number of cases, depending on what these underlying parameter values were. And I've only shown 3 here, but you get the idea. There's any number of parameter combinations for beta and gamma that would give you the same curve here and give you a very different surprise at the end when it came to the time of evaluating the intervention. So these problems, they're not going away, unfortunately, and what we need to have is good tools to deal with the uncertainty. And I think identifiability gives us one way of putting our models' structures to the test and seeing what we can expect from them, anticipating maybe the frustration that's predetermined in our destinies, and taking some steps to work around that by making suitable changes. And I think maybe that will do, I think.
Okay, thank you, Jason. Now we have a time for questions. If anyone would like to ask a question directly, you can do it, or maybe through me, you can ask the question in Spanish and I can translate if you like. Well, I cannot see anyone.
Susana,
¿Sí?
una
Dime.
pregunta más de tipo general. Pregúntale, por favor, cómo este tipo de investigación tiene influencia en las políticas públicas en Australia.
Yeah. Jason?
Yes.
Ivan would like to know how this, the use of these new tools is impacting on the public policies taken in Australia, if it's having any effect.
Yeah,
now
it's a
that
very good question. Yes,
well,
I think in a...
Sorry.
Oh, that's my timer. Okay, I think that we're maybe a little bit ahead of the stage where this is going to be influential in the policy sphere, but I think the time is coming, and I think that I can say that with a little bit of confidence, because about a year ago I was invited to this workshop with a whole lot of disease modelers in what was a residential workshop for a 2-week workshop in country Victoria. It's a very small town about 2 hours out of Melbourne, called the Matrix Institute, and it's a residential centre. And I was invited basically because I was known as someone in Australia who worked on identifiability, and I think that the disease modelers realised that they weren't really doing very much of that. So I think that the infiltration has started. I think that there is going to be a little bit of lead time, perhaps, because it's only sort of relatively recently that people are taking modelers seriously. So, and a lot of the modelers, I would say, are not particularly mathematical. So what we have to do is to get people comfortable with the idea of identifiability testing, and that it's going to increase the credibility of their models. And I think that the review paper that's in Epidemics with myself and another 17 people who are at this workshop is trying to push that angle, which is there's something in it for you to improve the quality of your models and the reliability and the regard that people will have for your models if you subject them to this scrutiny. So I think it's maybe at quite an early stage, but I'm hopeful.
Thank you. Iván, ¿decimos la respuesta o no?
Sí, traduce la respuesta, por favor.
Bueno, él dice que todavía ellos están más adelantados de lo que se está haciendo en política pública, pero que él está muy optimista porque solamente un año atrás que él estuvo participando de un workshop donde había gente que hacía modelamiento, estaban recién viéndose estas cosas, pero que él dice que ya la idea está infiltrada y que va a empezar a desarrollarse probablemente ya en ámbitos más públicos, ¿cierto? Porque se están tomando más en serio la importancia del modelamiento y que ese modelamiento tiene que ser confiable.